from the University of Stavanger here, and he is going to be telling us about the science of fission energy. So when you're ready.
Thank you, Alex. Welcome, everyone. It's a pleasure to talk to you today about the science of fission energy. My name is Alexander Rothkopf. I'm a theoretical physicist here at the University of Stavanger. And today I'm substituting for one of our international formally confirmed speakers who unfortunately, due to a personal reason, could in the end not make it to our symposium. So let's jump right in. But before we start to talk about fission, let me talk about an ingredient to fission that we have to talk about before, and that's nuclei. Nuclei are the cores of atoms, and even though they're only 1/10,000th of the size of an atom, they make up almost all of its mass, and that is because they are made up out of positively charged protons, red spheres here, and the electrically neutral neutrons, which are held together by the strong nuclear force. And if we refer, so for example, a proton and a neutron is around 2,000 times more heavy than the electrons that are whooshing around that nucleus, and therefore the core really is much more heavy than anything else in that atom. And if you want to refer to individual elements and their nuclei, we usually use a certain convention that I show you here. So we take a capital letter that denotes the name of the element. Because of things to come, I chose here uranium, a capital U. And what makes uranium uranium is the number of protons in its core, or conversely, the number of electrons floating around it. And that's denoted by this number in the subscript here, the atomic number, which for uranium is 92. Then we have a different number that's on the superscript, that's the mass number, and that denotes the number of protons and neutrons in that core. So you can have the same elements. I give you here an example of two uraniums with the same Z, but they may have a different number of neutrons, so a different mass number, and these elemental siblings we then call the isotopes, different isotopes of an element. And just to give you another example of a heavy element here with even more protons, plutonium with 94 protons. What we're going to do is we're going to try to make use of the energy that is stored in these heavy elements through the process of fission, and therefore we need certain elements that can undergo the process of fission, and these we call fissile elements, and this is why I selected those few here. Since energy cannot be created nor destroyed, we should, of course, ask, where does the energy in these elements come from? And if you conversely think, where do these elements themselves come from? I invite you to also have a look at tomorrow's talk by Anne-Cécile Larsen at 10 o'clock. And we had already nice talks by Francesco and Marianne on Tuesday on this topic. So now let's come to fission itself. And here I will talk, when I refer to fission, I mean the process where a nucleus of a heavy atom absorbs a slow neutron and subsequently splits in two, releasing in addition highly energetic neutron particles and electromagnetic radiation we call gamma rays. So let's go through this step by step. You have this, what we call a slow or a thermal neutron incoming. What do we mean by a slow neutron? Well, it should have a velocity of around 2 kilometers per second, which is the most probable temperature that you would find in a gas of neutrons at essentially room temperature. So now this slow neutron can impinge on a uranium-235 nucleus. Remember, that's the number of protons and neutrons in the subscript here, and it can wiggle itself into this nucleus, and by that it can form a uranium-236, protons plus neutrons in the superscript. In contrast to this rather boring-looking picture, that is quite a radical affair. This uranium-236 is pretty agitated. It's wobbling around, it's elongating, and what actually happens is that it's pinching a bit in the middle, and it rips apart, and then forms two daughter nuclei that we usually refer to as fission products that now fly out. And as one specific example here, I give you that outflies 141 barium and 92 krypton. If you add the mass numbers, 141 plus 92, you get 233. In physics, nothing gets lost. So where are those 3 units of mass between 236 and 233? If it flips, there they are. It's 3 neutrons that fly out of this process in addition to the fission products. And as I mentioned, there's also a lot of electromagnetic radiation that is coming out. I used here this specific example of barium and krypton, and I just want to put this figure here just with the message that you can take those 233 units of mass and somehow divide it up in a certain different combinations when you do fission. So there's different types of combinations of fission products that can arise from this reaction. Okay, this is fission, but we want to use it as a source of energy. So I should tell you about the energy budget. And the energy that is released from a fission event comes in the form essentially of kinetic energy of the fission products and what is called the decay products. And so to make a list here, I will use the unit of energy that is used in nuclear physics, and that's the mega electron volt. And I'll be coming right back to that one in a bit. So the kinetic energy of those fission products is around 170 MeV. Then there is the kinetic energy of those 3 neutrons, 5 MeV, and that gamma radiation also carries around 7 MeV. And in addition, those fission products, they decay themselves, releasing electrons and more electromagnetic radiation with a budget of around 13 MeV. And if you add all of this together, you get around 200 mega electron volts and, of energy out of one of these fission events. So what is 1 MeV? This is a unit that we usually are not used to in everyday life. If you just type it into Google, convert the unit, it tells you it's 10 to the minus 11 joule. So 10 zeros and then, so 0.10 zeros and a 1 joule. That looks like a very small number because you need 4,200 joules to boil 1 liter of water. But there's a lot of uranium nuclei in 1 kilo of fissile uranium. So if you could really fission all of that, then you would get 10 to the 12 joule. That's now a number with 12 zeros and an 80 glued in front. That's a pretty large number. If you compare it then to the energy content of 1 liter of gasoline, that's around 9 kilowatt hours, and that's 10 to the 6 joule. So there's a factor of 1 million between one of the theoretical energy content of a liter of gasoline and a kilogram of fissile material. I told you here that there are decay products playing a role. So let me say a few words about nuclear decays. I would like to focus on 3. The first one is alpha decay. And in alpha decay, a quantum fluctuation inside the nucleus upsets the delicate balance between the repulsive forces, the electromagnetic repulsive forces between the positively charged protons and the strong but very short-ranged nuclear force that is holding the protons and neutrons together. And that allows a cluster of 2 protons and 2 neutrons to escape the nucleus. And that is nothing but a helium nucleus. And historically, this was called an alpha particle. And so in our scheme, we are going down 4 units in the mass, and we're going down 2 units in the proton number. Now you can ask, when, as a student, can I start understanding this kind of process? And this is essentially in 5th semester when you start to study quantum mechanics, because that was one of the great successes of quantum mechanics, to understand that there's a process called quantum tunneling that allows this connection of 2 protons and 2 neutrons to tunnel out of the nucleus by overcoming a electrostatic repulsion barrier that they otherwise couldn't. Okay, so this is 5th semester. Now the next one is beta decay. In beta decay, a spontaneous quantum fluctuation changes a neutron into a proton through the release of an electron and an anti-neutrino. So here we keep the same number of protons plus neutrons, but you get 1 more proton in your nucleus. And when do we understand this? Well, this takes a bit longer, but then once you start studying quantum field theory, we now know really what's going on under the hood in this process, because the neutron is made up out of even smaller particles called quarks. And in this beta decay, one of those quarks that is a down type changes into an up type quark by interacting with what is known as a W boson that is associated with the weak force. And that W boson then decays into an antineutrino and electron. So this is understanding this is one of the successes of quantum field theory that you study, say, in your master's course. Then there's gamma decay. If your nucleus comes out of a previous nuclear reaction and again is quite agitated, it might relax to its lowest energy state by emitting a electromagnetic wave, a photon, and that is what we call a gamma decay. Okay, so we've talked about the one fission reaction. Now the question is, how can we use that to efficiently release the energy stored in fissile material? And for that, we need to sustain the fission, and that leads to the concept of the chain reaction. So we start out with our slow thermal neutron impinging on our uranium-235. That gives us 3 very fast neutrons. I told you that only the slow neutrons can wiggle themselves into the uranium-235. So what we need is a so-called moderator that is a material that has a lot of protons in it, because then very efficiently your neutrons can now bump into those protons, exchange energy and momentum, slow down. The moderator heats up, the neutrons slow down, and out you get again, slow thermal neutrons that now can actually induce subsequent fission events as they proceed. You see that there's some loss happening of the neutrons, but you can also see that if this chain reaction is very efficient, you get a lot of neutrons. So usually, in addition, you have some absorber control material present that absorbs some of the neutrons that come out, so that you keep the chain reaction steady, not petering off, but also not increasing in strength. Obviously, we need somehow this uranium-235 for the chain reaction to work in the way that I depicted it here. If you look at your natural uranium ore that comes out of the ground, it only has 0.7% of this uranium-235, and most of it is uranium-238 that is not directly amenable to this fission chain reaction. And therefore, you need to what is known as enriching, and that's where the whole enriching comes into play, the amount of uranium-235 in your fuel to around 3 to 5% before technically you can sustain such kind of a chain reaction. Okay, then, now I told you about the chain reaction. What comes out of a chain reaction is the following, and I would like to just give you a bit of a picture of what are the fission products that you can find after you're running this kind of chain reaction. So there's short-lived intermediate isotopes. For example, there's iodine, radioactive iodine, that is produced with a half-life of 6.5 hours because iodine plays a vital role in human chemistry, so body chemistry. This is an element that you might have heard about in the connection with nuclear accidents, for example. This then decays into a noble gas, xenon, which itself has a certain half-life of 9.2 hours. And to just remind you, half-life is the concept that denotes the time it takes for starting with an initial amount of radioactive material. It is the time that it takes for half of that material to have decayed. Okay, so this is hours of half-lives. Then you have medium-lived isotopes starting from europium with around 5 years of half-life to strontium and cesium-137 with around 30 years of half-life that you can find. And then there's samarium with around 88, so 90 years of half-life. Then there's very long-lived isotopes, starting from, say, technetium with 200,000 years of a half-life to cesium-135 with 2.3 million years of a half-life, and iodine-129 with 15 million years of a half-life. Note that the longer the half-life, the the slower the rate of decay. So the longer the half-life, the longer you have to watch this element, but the fewer decays of that happen in the time frame. Then there's obviously there's actinides around. Since we are only fissioning off the uranium-235, there's essentially most of the uranium-238 still in your fuel. And then around 1% of that uranium-238 gets transmuted into plutonium-239 and 240. And these are the isotopes that you have to then think about when it comes to waste treatment and such. Okay, so we've talked about fission, the chain reaction, the fission products. How do we now technically use this to extract the energy from the fission reaction? And this is, believe it or not, boiling a pressurized kettle. And that's the standard principle that we use in current nuclear power plants. Here is a rough sketch. Let me go through this with you. On the left, you see the so-called reactor vessel, the reactor core, where your uranium fuel, partially enriched, is sitting in there in the form of solid rods encased in a metal cladding. Then we said that we need this moderator material that slows down your neutrons to sustain the chain reaction. Here, that is water that fulfills both the role as a moderator and as heat transport medium that you heat up to very high pressures. You feed it into this primary coolant loop that is closed by itself. There's a heat exchanger with a secondary loop where you now create from that heat steam that drives a steam turbine to generate electricity. Electricity, yes. Then I told you, you want to make sure that the chain reaction is steady, not petering off, not increasing. And therefore, you have these control rods that are made out of neutron-absorbing materials that you can now insert into your core to stabilize the chain reaction. And because you're heating water here to very high pressures, you need a sturdy containment, even in normal operation mode, to contain this high pressure heat transport medium. Since we are supposed here to look into the future, let me mention some of the challenges that we encounter here. The challenge, for example, of solid fuel. We have an accumulation of the fission products inside the rods that you put inside your reactor. Because I told you about xenon, there's gases that are being produced. These can tend to induce cracks in addition to thermal stresses on these rods. And then you only burn around 4% of the material that you put into your reactor. So you have 96% of the original material still in there. And so you would have to think about either reprocessing it or discarding it in a safe fashion. Then there's the challenge of uranium fuel itself, because the non-fissile 238 uranium gets transmuted into 239 plutonium, and plutonium is chemically quite toxic. So not even from a radiation standpoint, you don't want to have that in your environment. And it's a nuclear weapons proliferation risk. So in the future, if you want to build nuclear reactors, you would like to address some of these issues. And so let me just bring up one alternative that has received some attention quite recently, and that is molten salt reactors, where now the fuel and the coolant medium are one, either uranium or thorium-based liquid salts. And so here now you have a primary loop in which now this say thorium liquid salt is circulated through your reactor core. Because the fuel is liquid, you will now put your moderator usually as a solid element in your reactor core through which you cycle this salt. You have your control rods still in there because you still want to keep the chain reaction well balanced. And then you have a heat exchange infrastructure that allows you then to transfer the heat now from your fuel, from your thorium salts into other salts, and eventually again to water, so that you can then drive a steam engine to generate electricity. What are the advantages of such kind of a reactor design? Well, because you're now not using water under high pressures for transporting off your heat, this setup actually operates under atmospheric pressure, which means you need much less containment when the reactor is operating under normal conditions. There is the so-called freeze plug design, because your fuel is now liquid, that is based on the second law of thermodynamics and gravity, that are quite reliable partners. So essentially what it is, it's that you keep artificially frozen a vent in your primary loop, and if in an accident condition the electricity cuts out, what will happen thanks to the second law of thermodynamics, that will melt that plug, and because your fuel is liquid, it will drain off thanks to gravity being present into a non-critical configuration below the reactor. Of course, there's no free lunch. There's of course challenges associated with this concept. One thing is that you need online reprocessing of the salt as it cycles through your reactor, because you're accumulating, of course, the fission products there, and you need to separate those off. And since now you're having your fuel cycle through your primary coolant loop, the materials that you use in that loop experience much harder radiation stresses than what you would have if you cycle through water through a regular reactor design. Okay, so if we then say, what are the opportunities for physicists and physics students in the future in this field? Well, let's start by looking at opportunities to improve today's design and today's reactors by a better understanding of nuclear fuel. One item here is to think about how can you devise fuels with a higher burn-up ratio, so to get more of the material burned up during its time in the reactor. Then you want to better understand the formation of defects in your fuel rods, and there's a lot of experimental work going on to get a better microscopic understanding of the defect formation in conjunction with the multi-scale simulation of, say, heat transport and radiation. And there's a very long-term work ongoing to develop safer fuels by developing ceramic enclosures for your fuel that then houses small pellets of the fuel in a ceramic housing that then will contain the fission products and also the fission gases in these small pellets. And the ceramics make them sturdy against high temperatures. And so here I would say that there's a lot of collaboration opportunities between materials physics and nuclear physics experiments together with the multi-scale physics simulation community to improve on current reactor designs and fuels. Then there's developing the molten salt reactors. That is really from scratch, from fuels to structures. You need to understand the molten salt fuels, characterize their basic parameters. Then you want to, and you have to develop this online processing where you need to utilize both nuclear and chemical properties of the materials for a safe and for a safe treatment. And not to be underestimated, you need corrosion-resistant piping, and for that you need to develop new metal alloys and ceramic compounds to withstand the radiation pressure in these designs. So there, a lot of material physics and physical chemistry opportunities are abound. For me, as a theoretical physicist, maybe I would like to, in this last slide, take a slightly longer outlook and ask, well, if we want to eventually use the energy and nuclei in the context of energy with a similar versatility that we now use chemical reactions that we have over the last 100 years, thanks to the interplay between physicists and chemists, gotten such a good control over, we should think about how do we get a similar versatile control of the nuclear degrees of freedom that we now have above the electronic degrees of freedom. And you can think about many different venues here. One is improving a precision determination of low energy nuclear transitions that can be used in applications, for example, nuclear clocks or nuclear batteries. And for that, we need to better understand the structure of nuclei. Then there is a large-scale European facility coming online, the extreme light infrastructure, where very high laser and high-intensity lasers are being built that promise to open up the research field of laser-induced nuclear reactions. So just as the regular lasers helped us to become versatile with electronic structures, now we have a chance to go in the direction there with nuclei too. And again, as a theorist, that of course means that there is a lot of need for new theory to understand this high intensity laser field interactions with nuclei. And so there's a lot of basic nuclear physics opportunities, both in experiment and theory, out there if we think long-term about how we want to utilize nuclei and the nuclear degrees of freedom in the context of energy. And with that, I will just conclude. I showed you several of the opportunities that I personally believe are out there, usually coming in a combination of collaboration between material science, nuclear physics, simulation physics, and on the long term, also really basic science, nuclear physics. And with that, thank you for your attention.
Thank you, Alexander. People with questions, welcome to put them in the Q&A session. We have one question now from Tina. It says, how can one convince governments again to allow for nuclear methods for energy production? Seems like the research is still going strong. However, the governments abroad have been able to use these new explorations.
Coming back to this morning's speaker, I should refrain from commenting on things that I don't know about. And I will play this card now, because the only thing that I can do as a scientist is go out there, explain the mechanisms, then talk to my engineering friends who can then tell me about the feasibility of implementing and realizing these principles. And then what we can do is we can offer the general public a possible technological solution. And then it's up to the general public to have a conversation, because it needs to be the general public that feels comfortable with these technologies. And that means that I have to go out there and give a balanced, nuanced view of the benefits and potential risks of the technology. But in the end, it is then the general public that has to decide, is this a form of utilizing energy that we want, factoring in, as we heard this morning, all the different components. What's the context in relation to climate change, for example? Are there other economic or ecologic aspects that benefit or can be seen as a drawback to a certain technology? But in the end, we can, as researchers and engineers, put forward a possible solution that we think is a solution from our side, and then it has to be the general public that needs to decide whether they would like to jump on the bandwagon or not.
Another question. At the beginning, you showed this cartoon of a neutron coming into a nucleus, and then the nucleus does some things.
Yes.
Presumably there is a model for exactly what the nucleus does. And my question would be, are we in a position now, without looking at experimental data at all, to be able to tell which nuclei will fission from just knowing the masses of protons and neutrons and their properties, or do we still have to refer to experimental data to calculate?
The audience in the room, in the Zoom room, may want to add to what I'm about to say, but I believe that ultimately we still need phenomenological input for heavy nuclei. There has been a lot of advances for light and intermediate mass nuclei using modern concepts such as effective field theory, where one essentially identifies, so to say, the relevant small building blocks, and then has a clever way how to build up larger structures from these relevant small building blocks. But I think, as far as I know, if you go then to very heavy nuclei, these methods are still overwhelmed, and therefore we still are in need of phenomenological input when it comes to, for example, and so if we want to compute a fission process like this,
uranium, for example.
Yes.
Yeah.
Yes.
Another question from Gerhard: are there experimental molten salt reactors being built, or is it still too early for that?
So there were already molten salt reactors being built, but actually you can go to the Shanghai Institute for Applied Physics website, and maybe you go just to the Wikipedia webpage where I found this link, and then go to this institute, and you will see that China has invested a lot of resources in realizing thorium-based and also molten salt reactor designs. They have a pebble bed reactor design at the Tsinghua University is developing, and they have the molten salt reactor design that this institute in Shanghai is tasked with developing. And they just put, I think last year, a test reactor online. Obviously, I'm not an expert directly in the technology side here, but it seems that this is a running experimental facility.
Okay, we have one more question from the Q&A from Sajida Ahmed. The point about using lasers and nuclei, how is this different from inertial confinement fusion, where a high-intensity laser is focused on a Hohlraum target?
Yes. So in inertial confinement fusion, I think you're using the pressure generated by these extremely intense lasers to actually fuse nucleons together. While here, what you're really trying to do is you're trying to access transitions within a single nucleus. So it's not about smashing the nuclei or small parts of the nucleus together. So the inertial confinement fusion is using light elements to fuse them. And these experiments that I was referring to, upcoming experiments, they're taking, say, a heavier nucleus, and they're trying to excite the different levels inside that nucleus without, say, destroying that nucleus, and utilize, for example, the energy that you then store in this transition, for example.